No? Okay, good. Okay, my name's Bernard Blackham. I'm from the University of New South Wales. I'm here to talk to you today about protected hard real-time and what we can do to actually make this a reality. So, a bit of background. We have traditionally hard real-time systems which are developed using this methodology. You have one CPU that handles your application, might handle your GUI, and if you have any tasks that require hard real-time deadlines and need to be isolated from the rest of the system, then what normally happens is you create a second processor, separate to your main processor, and you put your hard real-time task on the system. You might use a real-time operating system, and the purpose of doing that is to isolate it from anything that might interfere with it, anything that might crash it, or anything that might cause it to miss its deadline. In this scenario, the deadlines are actually the most critical thing.
You told I have to use a microphone.
What we're proposing is to use a model where everything is consolidated onto one processor. And this model has been suggested previously. It was suggested almost 10 years ago now by McNutt and RTSS, and many others. It's the standard consolidation argument, and it has many advantages. The advantages, they're fairly obvious. If you have less hardware you need to design, it brings down the cost and complexity of the system. Things get simpler. I don't know, has anyone tried to debug a system with several different processors all communicating at the same time? And there's a bug, and you have to deal with several debuggers. It's actually quite involved. So it's pretty easy to see that there are advantages to this model. We've seen it happen on a lot of systems already in the server market. It hasn't taken off yet in in hard real-time yet. And I can see two reasons why this hasn't happened in hard real-time. One is that there is a single point of failure now. If you consolidate everything onto one CPU, the supervisor or the operating system on that CPU, if that fails, then everything is crashed, corrupted, and game is over. So that single point of failure, if we're going to use this model, cannot crash. The other problem with this model is that as soon as you start throwing lots of systems onto one CPU, the schedulability of the CPU becomes difficult to reason about. There is theory to say if the system is schedulable, but it all depends on if you can give worst-case execution time guarantees of every task running on the system. If you can't specify how long something will run for, then you can't do any of this. So we propose that we can mitigate these two problems. The first one is our trustworthy operating system. You might have heard of a microkernel called SEL4. SEL4, it's a general purpose microkernel, but the biggest feature of it is that about 2 years ago we managed to finally prove that the C code of SEL4 conforms to the specification of what the kernel will do. And the specification doesn't say things like it will crash or it will allow buffer overflows. So SEL4 gives you a very strong assurance that the platform that you're building on top of isn't vulnerable to all these classes of vulnerabilities and bugs. What it doesn't give you is timing correctness. For a hard real-time system, we also need to be able to give you worst-case execution time guarantees so that you can handle interrupts within a certain guaranteed latency, and you can compute your worst-case execution time of your tasks. So, first one is solved, that's been done. The second one is what I'm here to talk to you today about. So we need to somehow get worst-case execution time guarantees from the SEL4 microkernel, or any microkernel. And this, as far as we know, hasn't actually been done before. People have done it for simple operating systems. Any operating system with protection and context switching, it's very hard to give worst-case execution time guarantees. And I'll tell you a bit about why SEL4 is easier to give worst-case execution time guarantees on. Firstly, it's a microkernel, so it is small. It's a very small body of code. The microkernel is also what's called an event-based design. In other kernels, you have what's called a process-based design, where you have each thread running on the system has a separate kernel stack. And when you switch between threads, you need to change your stack. And almost all the static analysis tools out there, just as soon as you change your stack pointer, they just they have no idea what's going on because all your context changes, you can't use any information that you had previously. In SEL4, you only have one stack, and the C code of the kernel reads like a standard C program. There's no magic stack switching that goes on. And this makes static analysis much, much easier. Also, SEL4 runs when you're inside the kernel, interrupts are turned off. And this makes it much easier to reason about formally. However, it does increase your execution time because you can't handle an interrupt until you exit the kernel or you reach a preemption point inside the kernel where you check for an interrupt, and if there is an interrupt pending, you can go handle it immediately. So this design of SEL4 has made it much, much easier to analyze for worst-case execution time than other kernels that we've looked at. So we wanted to actually compute the worst-case execution time for SEL4 to give some guarantees. This is our evaluation board. It's a Beagle board that you might have seen. It's based on an ARM Cortex-A8 processor. The A8 is quite a complicated processor. It's got branch predictors, several levels of caches, it has a dual pipeline. There's a lot of complications there which for our preliminary analysis we have turned off. So we currently don't support data cache, we're working on that at the moment. Branch predictors are off, but again there is research out there to do this, so we believe that this is not a hard problem to solve in the end. But we are dealing with instruction caches. So to create a system which you can construct hard real-time systems upon, this seemed like a good target. So the analysis works a bit like this. We start off with the SEL4 binary, not the C code. We're working with the binary because that takes into account all the compiler optimizations that might have taken place, takes into account the program layout of the program itself, of the kernel itself, and the cache line layout. From this, we extract the control flow graph of SEL4. At the moment, we also have to specify all the loop bounds for every loop in SEL4 by hand. A lot of this can be automated, but for now, we've done it by hand because it was simpler to start with. And we also have the system model, which is the model of the pipeline in the processor, the caches of the processor, and just the general microarchitecture of how the Cortex-A8 works. And so all of this was fed into a tool called Kronos. Is that a question? Can we hold questions till the end?
Yeah, there will be 5 minutes for questions at the end.
I'm on a deadline too. So Kronos is a tool from the National University of Singapore. It's designed to compute worst-case execution times, and what it does is it aggregates all this information and gives you a set of equations. And if you can solve these equations, then that will give you a worst-case execution time. So we adapted Kronos to the ARM architecture and our platform, and we've used it to analyze SEL4. So our results, they look a little bit like this. Analyzing the entirety of SEL4, and the first thing that came out was this number, 686 milliseconds. Unfortunately, there aren't that many hard real-time systems around where this is acceptable. It's quite a long latency. Maybe for Kai's backup solutions this would be fine, but for most hard real-time systems this is not really acceptable. So we dug into what was causing this, and in SEL4 it was a deletion scenario. So in SEL4 you have these IPC primitives for doing communication called endpoints. Lots of different threads can block waiting for a message on the endpoint. And if you're a malicious user and you have the ability to create 100,000 threads, you can get those 100,000 threads all waiting on this one endpoint. And when you delete the endpoint, the kernel has to go through and dequeue every single thread